I want to introduce my partner and the little brother I never wanted. But the what exactly? Our founder and keeper of the flame, Paul Dix. So.
All right, there we go. Hello, everybody. Thank you for coming here today into the financial district of New York. The New York InfluxDays I actually really love because I live in New York. I live in Williamsburg, but I spend probably about anywhere from a quarter to half my time elsewhere in the world, particularly in San Francisco. So I like it when I get to stay local. So today I'm going to give an update on Flux and InfluxDB 2. I'll introduce the concepts really quickly. I'll try to get through the introductory stuff as quickly as possible because I know plenty of you already know that stuff. And really what I want to do is talk about where some of this is going and talk about some of the open questions that we have that we still want to resolve in the language design of Flux, and things that we would actually very much like to talk to you about over the course of the next 2 days. All right, so Flux, what is it? It is, we're calling it a data scripting language. It's a programming language, yes, but specifically we want to make it useful for working with time series data, but also working with data generally. The style of it is very functional. It's MIT licensed with no caveats or anything like that, so you can use the code and do whatever you want with it. It is a combination of, like I said, a language, but it's also a virtual machine, a query engine, a query planner, and a query optimizer. So all of these things are kind of baked into one thing. So the thing that I think is really interesting about it and makes it a bit unique is this idea that it is a language plus a query engine, right? So we can do things like we can optimize scripts that you write for the specific data sources that we're connecting to, and I'll show some of that in a second. So Flux lives in its own repository, which is a new thing for us. We did this actually about a year ago, and we decided, like, over the course of developing Flux the language, we realized that originally we started with it'll be a new query language for InfluxDB 2. And then we thought, okay, well, we actually want more than just a query language. We want to be able to define more complicated processing tasks like you can do in Capacitor. And then even beyond that, we realized, why even tie it to InfluxDB? Why not be able to pull in data from other data sources and work with it? So we realized that as a project, Flux's scope is actually larger than the scope of InfluxDB. So why not separate it into its own repo so it can have a life of its own, kind of like Telegraph has a life of its own outside of InfluxDB, right? Telegraph can be used all over the place, even without Influx. And we hope and expect that the same will be true for Flux, the language. So now let's talk about InfluxDB, specifically 2.0. So 2.0 represents the biggest change that we've made to the database since we went from the 0.8 version in November of 2014 to 0.9, which wasn't released until June of 2015. So that change basically introduced the schema that exists today with measurements, tags, and fields, which was a breaking change from 0.8. That was the big difference. But the difference between the 0.8 to 0.9 migration and the 1.x to 2.0 migration is there will be a clean migration path. The functionality in 2.0 represents a superset of what you can do in 1.x. And what we're also building is a compatibility layer. So even though 2.0 features an all-new API, you will be able to talk to a 2.0 server as though it were 1.x. So you'll be able to write data in using 1.x client libraries, and you'll be able to put InfluxQL queries against the server. Even though Flux is the language we're focusing on for the future, we need to be able to support InfluxQL for all the people who have, a bunch of code written around that. So InfluxDB 2 is also MIT licensed, just like before. The entire API in it is designed to be multi-tenanted, right? The InfluxDB 1.x API had a concept of a user and a password, and that was basically it. In 2.0, there's multi-tenancy kind of built into the API at a top level. Importantly, we're taking the different projects of the tick stack, Telegraph, InfluxDB, Chronograph, and Capacitor, and we're rolling them all into one binary. Now, you'll be able to separate them out, but what this means is for people who are just starting out and playing around with it, they can install one thing and immediately have data collection happening, a user interface, writes, queries, and background processing for monitoring and alerting. Just like before, everything we do in the single server is open source. It's MIT licensed. You can do whatever you want with it. As Evan mentioned, we are working on a cloud-based offering. Importantly, the new cloud-based offering will have usage-based pricing, right? Similar to AWS, where you pay for query compute time, you pay for network bandwidth, and you pay for storage. And as I mentioned, because the 2.0 API is multi-tenanted, our cloud service will be designed to be multi-tenanted as well. But for those who want, they can get dedicated capacity within the multi-tenanted system, right? So they can guarantee that they have some capacity withheld that's only for them. And obviously, we'll have later an enterprise on-premise offering that offers scale-out clustering, the ability to do query processing, to scale query processing from storage, from background task processing separately. And the thing between all of these things is there's one consistent documented API, right? There's a single API for defining data collection rules, for writing data, querying data, for defining stream and batch processing jobs, storing user dashboards, configurations for collectors, all of these sorts of things, right? Right now, we have 4 different projects, and each of them has their own kind of configuration file, their own API, and they're not totally consistent. So what we wanted to do with 2.0 was pull them all together and just have one consistent experience across the board. And this entire API is defined in the InfluxDB repo right now in this Swagger file, right? So we're just using the open API spec to define what that is. And what that means is for any language that supports Swagger, which is pretty much most of them that I can think of, you can actually generate a client library and work with the API right there without having to write code yourself. But even though you can generate a client library, oftentimes what you get from those generated files is pretty basic. So there's a lot of extra stuff you have to do. So we're going to do that ourselves. And we're going to write wrappers around that to make it a little bit more usable. So this is new for the 2.0 effort. In InfluxDB 1.x, we actually didn't write any of the client libraries that people out there in the world are using, for the most part. We basically just created the server, had the API, the HTTP API available, and we told people, like, that's what you use. Good luck. Right? Like, whatever you want to use it in, you're going to have to write the client library. And really, that was a function of our resources at the time, right? We wrote the database, and it was just me and a couple other people, and we didn't have time to write client libraries for all these other languages. Now that we're farther along, we're going to officially support Go and JavaScript right out of the gate. Ruby, Python, PHP, Java and C# will all follow shortly thereafter. Actually, Java is currently being worked on right now. So we will have officially supported client libraries by us, and ideally, they will look consistent across each language. The function calls will be the same, that kind of stuff. I mean, we'll use language idioms where appropriate, but they should have a sort of like consistent look and feel. We're also creating visualization libraries. So we actually already have an NPM module out there for basically building visualizations. And we use this within the user interface for 2.0. Obviously, that UI used to be called Chronograph. Now for 2.0, we've pulled the visualization stuff out as separate libraries because we want to make it easy for developers to create their own user interfaces, right? Our UI is great if you want to do some basic exploration or dashboarding, but we want to enable you to build custom user interfaces that you show to your users. And we want you to be able to use the exact same libraries and tools that we use to build our UI. So let me talk about multi-tenancy really quickly. So with multi-tenancy, you get into this concept of there are different roles for people who are using the system. And I think that's helpful to think about because they're different depending on whether you're using our cloud, whether you're operating enterprise, and whether you're a user. So the first is an operator, right? This is the operator of a cluster. So in our cloud, that's us. In enterprise, that's probably some of you, right? Running it for your organization and operating it. There's an organization administrator. So everything within the InfluxDB2 API is tied to an organization. You create an organization, and that's the base level. That's basically like a tenant, right? So you can have an administrator of an individual organization, but they won't have control over the cluster as a whole, right? They won't be able to create their own orgs or all this other stuff, but they will be able to manage stuff below that. And then finally, you have users, right? Users are the people who are writing data, they're doing queries, they're creating dashboards, they may be defining tasks, and there are ways that you may want to limit what they can do within the scope of an organization itself. So the data model for 2.0, this isn't by means complete. There's more to it, but these are the big, important, high-level concepts, I think. So as I mentioned, you have a concept of organizations. Beneath organizations, you have what we're calling buckets. And a bucket is basically the combination of a database and a retention policy put together, right? So a bucket has a period of time that you're going to keep data around. That could be forever, it could be for a week, it could be for a day. And one of the reasons we're calling them buckets is because database is kind of a loaded term. Some people, when they think about database, they think about the files on the file system, and that actually means something. Buckets don't necessarily map directly to specific files on a file system. And one of the design goals was we wanted within a cluster to be able to have thousands of buckets. So underneath a bucket, you have the actual time series data that you're going to be keeping around, right? You have tasks. So tasks basically are background or stream processing jobs. This is basically the capacitor functionality. Tasks are written in Flux, and you tell the server, run this periodically on some interval or stream data into it. So one of the common bits of feedback we've gotten with capacitor, it's very hard to debug. It's very hard to see what's going on in the system. So within the API, we want to enable people to see what's going on within the task system and to be able to fix things if they get broken. So part of the API is, and part of the implementation is when the system is running tasks in the background, it keeps logs about what's going on. And these are called runs. These are individual runs of a task, right? So you define a task and say you tell it to run once an hour. Each time it runs, you will have a log of that run. What happened, was it successful, and what was the output, right? So you have the runs themselves, you have the logs, which is if it actually throws some sort of error, you can capture that context and you can view it either through the user interface or pull it back from the API. You have dashboards, obviously. You have users, which are actually, in this case, this is people pointing and clicking in the UI. So generally speaking, these people will be tied to an actual user account, right? And then beneath them, you have tokens. So tokens are what you use for API access. So basically, when a user logs in, they're granted a temporary token that they use. Everything you do in the UI, in the web UI, is driven by the API. So that means anything you're clicking on doing in there can be driven through the API via a token. And tokens have authorizations, which is what are the things they're allowed to do in the system, right? Are they allowed to create a dashboard? Are they allowed to edit a dashboard? Are they allowed to create a task? Are they allowed to edit a task? And then you also have this was called protos. I think the name changed, but they're basically templates. So the idea behind a template is you can have a template for a dashboard, for example, and there are variables that you just plug into that, right? So if you have like a dashboard, for a system dashboard for a specific host or something. You have scrapers. So this is new in 2.0, which is it supports both push and pull out of the box. So you can scrape targets directly from the database itself. Right now, if you want to do scraping, you have to integrate, you have to configure Telegraph to do the scraping and then push the data into the database. In 2.0, you can actually specify Prometheus scrape targets and scrape all of them right out of the box. We will also support the Open Metrics standard very soon. So basically, Prometheus and Open Metrics will be supported as a first-class citizen in 2.0. And you have Telegraph configs. So in the UI, there's actually a way to drill down and create a Telegraph config based on the plugins you want enabled. The new versions of Telegraph are actually able to connect to a remote InfluxDB2 API, whether it's in the cloud or enterprise service or an open source server, and pull down a config that they can use. And then finally, you have labels. So labels are basically a way to organize any resource in the system. These are very similar to how Kubernetes uses labels. So you can assign labels to things. So you could have a label for, say you have a label for Redis, and you could associate that label with dashboards associated with Redis, but also tasks. So you'd very simply be able to say, okay, what are all the things I have? Dashboards, tasks, alerts, all sorts of things that are associated with this particular label. So now let's talk about Flux. I'll give a quick intro to it, and then I'll go into some of the open questions. So there are multiple ways to run Flux as a language. There will be a command line interpreter, so you can actually run it like you would Python or Ruby or something like that. InfluxDB 1.7 has a preview release of it, and obviously in 2.0, Flux is there. So there's a spec for the language, and it's fairly detailed. This is all up on the repository, InfluxData/Flux, and you can see in there all the details about how the language is supposed to work. In theory, somebody could actually take that spec and create an implementation of Flux themselves. So here are some of the basics. First, I want to show a query, right? So basically what we're doing in this query is we're getting all the data from our Telegraph bucket for the last hour, and we're filtering it by the CPU measurement and the usage system field. And you can see here that we have comments are a thing in the language. We have string literals, or named arguments rather. We have string literals. As I mentioned before, we have buckets, not databases. So that's what we're calling them. And also with 2.0, if you end up migrating 1.x data, the mapping that it creates is what you see here, which is the bucket name becomes the database name / the retention policy. But there's no requirement that a bucket name has to have a slash in it. It can just be a string of characters. We have duration literals as a first class thing in the language, right? You don't have to put them in quotes. Time literals also. We have this funky little pipe forward operator. As I mentioned, the language is functional. And the thing is, like, one of the things about functional languages, if you want to do a pure functional language, what you end up doing is you end up creating like a Lisp, right? Except for, I think Lisp is a bit of a nightmare because there's all this like nesting and all this other stuff. So the thing that the pipe forward operator does is it enables you to create a functional language where things read more sequentially, right? So basically this is take the output from the last function and send it into the next function. This is something we borrowed from Elixir. Also, there are anonymous functions. In this case, we're doing a filter of the data. So here we're showing like a predicate function. So basically, you can see like the OR operator, the AND operator. So this predicate function is used style of function is used specifically for filters. We have variables in the language and obviously different types, integers, floats, strings, durations, obviously, times, arrays, objects. There's some other more complex types that are actually core to the language, which I think will be easier to show through a little bit of code. So you can define your own functions, and this will highlight a couple of different things. So here's us defining a function that can be pipe forwarded to, right? So basically all this function does is it takes the values in all sets of tables and it squares the values, right? So we call it square. We say it takes an argument with the default value of something pipe forwarded to it. So the argument name is tables. Equals means we're going to give it some sort of default value, and then that funky like less than dash is basically I can take something that's pipe forwarded to me. Now you could actually call this function by specifying square and then the argument tables, or you can pipe forward to it. So tables are basically like a high-level concept. There's basically like streams of data, right, that you're working with. And these are just different tables of data. And this is really how Flux, the query engine, sees all of your data. Remember that in InfluxDB 1.x, you have this idea of measurements, tags, and fields. In Flux, once the data gets to the engine, it really doesn't need to make a distinction there. It just thinks of tables of data, which it's a bit easier to work with. So here we're mapping over the individual records in each table that gets sent to it. And then we're squaring the value. So this with keyword is actually potentially new for those of you who have already seen us show off Flux before. Basically, the idea is you just say, we're taking this object and we're working specifically with the value key, and then we're going to update that key, or the value of that key in the object. So here's how you call it, right? From range for the time range, filter for filtering based on, the metadata, square it, and then potentially we could filter again, right? Or do whatever we want. And this functional style, I think, is pretty nice because you can do things like this, like chaining these operations, and it just becomes trivial. And you can define new functions like this. So data sources is a big thing in the language. As I mentioned, Flux isn't necessarily just tied to InfluxDB. We want you to be able to pull in data from any number of sources. So it could be a MySQL database, a Postgres database, Redis. It could be a file on S3 formatted in JSON, XML, if you're an unhappy person, or CSV. Right, so the idea is we have data sources for many different things. Now, right now we have InfluxDB is obviously a first-class data source. We have basically a prototype of a SQL data source, either Postgres or MySQL, and we also are able to pull basically from CSV files local on disk. The CSV file stuff we actually use extensively in our testing framework for the language to test functions to see that they do what we expect them to do. And then finally, you have data sinks, right? These are the outputs. So in normal InfluxQL queries, you don't have data sinks at all, right? Because you're only issuing the query as a batch query, and the result gets sent back to you, the user. Where data sinks become interesting is when you're doing background processing, right? Where capacitor lives right now, and where the tasks subsystem in 2.0 lives, which is we're doing stream processing, we're doing batch processing. Data sinks are interesting if you're going to do ETL, if you're going to do things like offload data to some other third-party system, if you're going to do transformations and pipe it back into the database as basically like a materialized view, or if you're going to do monitoring and alerting where you're triggering something against a third-party system like Slack or PagerDuty or something like that. So let's walk through a quick task example. So tasks, basically, they're like continuous queries in 1.x, but they're way, way better. And we're focusing a lot more effort than on tasks than we did on CQs. And they're way better essentially because of Flux, but also because of, as I mentioned, the debugging stuff that we're building into the implementation, into the database of keeping logs, but also in the tool chain for developing them, right? The CLI, which will include like a test runner and the ability to incrementally create your tasks. So here's a task. So as you can see here at the top, we have this option syntax. So this is in the language. Basically, you can specify the information for the task. And the goal with putting the option syntax in the language like this was that we wanted basically everything you needed to be able to understand what a task is doing and what its behavior is to be stored in the single like script that defines it, right? As opposed to having like a separate configuration file for a task outside of the actual script. So here we can see we have the task itself. It has a name, it has a cron. So that's one thing is you can use cron style scheduling to determine like when a task will run. But you can also use, more simple, just like using every as an option and specify like a duration, like run once a minute or run once an hour or whatever. Packages and imports is a thing in the language, and I'll actually talk a little bit more about this in the open questions section. Map, obviously, I already showed that with the square. String interpolation is built in there, right? So you can build messages or you can build messages to an email system or whatever. Ship data elsewhere, right? So here we imported from the SFTP package. It has a method called to, which will send a message to these other things. Another thing we're building in is this load secret function. So this is a top level function in the language. And the idea is that anytime you're going to connect to a third-party data source, either source or sink, you need to have authentication information stored somewhere. In the open source 2.0, you can store it in basically just in the key value store locally, which is not what we recommend because it's all just in plain text. Or you can integrate it into a system like Vault, right? A third-party secret store. So on to the open questions part of the talk, my favorite part. So one big one is around user packages and dependencies. And I guess a few years ago, I didn't really, or maybe more than that, I didn't really appreciate how important this question was until I became a Go programmer. And they did not solve this problem for us. And it has been an incredible pain for years. Right, so I do think that's something that, it should be, packages and dependencies need to be a first-class citizen in a language. They need real consideration, and I think it's important to actually think about them ahead of time and provide the system for doing it, right? In Ruby, like I started using Ruby back before Gems was actually totally included in it, back before Bundler even existed. And I grew up in the Ruby community as they actually developed that whole system. I recently learned Rust, which has a package management system called Cargo. Cargo was actually built by Yehuda Katz, the same guy who built Bundler in the Ruby community. And I think Cargo, to me, Cargo is basically the gold standard for how a package management system should work and how it should help the users develop code in packages. So basically the questions is, how do you build them out? How do you handle versions? And how do you handle dependencies, right? So here are some ideas around that. Some of this we already have, mainly for the standard library, but the versioning stuff is still kind of like up in the air. So here, basically the idea is we have a package called Paul, and basically within this package, like within a directory, you define a file, you create a file called package.flux. And that is the file that it will look for if you do an import of the Paul package. We have a version specified at the top. It's actually in the code. And then say we wanted to define that square function that I was talking about earlier that I showed, right? We could define it right here in the package.flux file. So the entire package is one file, it's self-contained. Or we could use a set of files that are in this directory or in subdirectories and put them together. So the idea here is we import packages, which is basically just something that would be in the standard library for that has some helper functions for putting together packages. We tell it to load these files. Each one of those files will also need to have the package Paul declaration at the top. They must not have a version, right? The version must only be specified here in the package.flux file. Or we could do something like this, which would be just load it from like some matcher, some glob matcher, right? So later, when we want to use this package, we could say, okay, we're going to import the package. And remember, as I said, everything in 2.0 is scoped by an organization. And the idea is we're going to have a package manager in the 2.0 API, and the packages in the package manager will be scoped by an organization name. So in this case, I've called it my org, some generic name, and Paul is the actual package. So I haven't specified a version or anything like that, so it's basically just going to look for the latest thing. And here I have an example where I have some data, you know, a set of tables, and I just pipe it forward to the square function to call it. So another way is I can specify the specific version that I want, and I would do this actually in the import itself. This is different than where I've seen elsewhere, right? Usually you have the version specified in a configuration file. Curious what people think about this, actually putting it in the import statement. And the idea is there are a few different ways it would go to look up where this package is, right? First, it would look in flux home /myorg/paul for /package.flux. If there's one there, it would check to see if that version matches. If it doesn't, and if flux home isn't set, then it would skip to 3. Or no, if it doesn't match or if there isn't one there, it would look in flux home myorg paul version number /package.flux. And then finally, if it's not there, the default place, this you can specify by configuration, which is where's the location of the package manager API. So we obviously will have a package manager API that's hosted for the entire community at cloud2.influxdata.com/API/v1 packages, and that's where it would look, right? And then you can go ahead and call it. So what this execution order does is it makes it so that you can be developing this package and testing it out locally on your system. And then when you're happy with where it is, you would be able to submit that package to some public package repository with the set version. And then other people can use it. So the idea is you can move seamlessly from local development to publishing it officially. This is actually like originally when we were doing 2.0, I was debating like, do we really want to do a package manager, right? Maybe we shouldn't be doing a package manager and we should just like have it be from source code and stuff like that. And I realized after a while, I actually, based on my experience with dependencies in Go, I actually hate the idea of importing directly from a repo. I think it's horrible. I actually like the idea of having a repository separate from the actual packages, I mean, normally in a compiled language, the actual compiled assets that you use. I like that separation. And honestly, like this would, if this existed, if Go had that and that you couldn't import from a repo, I feel like it would eliminate a million problems. But that's a debate we can have this evening over, over a cocktail hour. So then the other one is basically like at least this version, right? So basically import at least this version, you assume like you're not going to make a breaking change. Okay, how do we do error handling? This is really an open question because we don't even have, like with the package management stuff, we've at least started some of the syntax is there, the standard library is already being built out. With error handling, it's really open. So for example, say we're going to send a message to Slack. We import the Slack package, and we say send, you know, to the foo room this message, and here's the token that you use to authenticate it. So obviously we're calling out over the network. What happens if an error occurs? What do we do? So if there's that return value, So obviously, you can do like multi-returns. You can do like Go does with like nils or whatever. One question we have is, should we use option types? You see this in functional languages. This is in Rust, obviously, which is you wrap the return value. You expect some sort of result, and you wrap it so you can match against it, right? So we could have, for instance, matching syntax like this. So we match on the return value, and we say, OK, on error, do this. And here in this example, what I'm doing is the return value right now is basically an option type, right? And once we do the match, we change the binding to return to be the actual thing that we have, right? So on error, return, and at that point, it is already an error style object. So you could work with it as though it's an error, an unwrapped error. Else, do something else, right? So else is basically like the default catch. But you could, so, and then like, again, like with the return thing, it would be whatever it is that's going to return if it's not an error. I'm a fan of the match style syntax. It is, originally one of the design goals of Flux was we wanted to keep it similar to JavaScript. This is obviously a departure from that. I'm a fan of the match style syntax, but one of the other questions is like, if we're going to have this, do we force users to unwrap errors? If something can return an error, do we force users to unwrap them? Or do we have some sort of implicit unwrapping so that they don't necessarily have to do a match all the time if they don't care? Loops. Do we need like imperative style loops in the language? So as I said, the language is functional in nature, but if you have like recursion and you have reduce functions, you essentially can do all the things you would do with loops. Mainly for me, it's a usability question. Like, is it understandable for people to use the language without loops? So basically, take, for example, we have these records. If you want to iterate over them, I think just iterating over them is pretty straightforward, right? I think people can understand the map thing. Computing a sum on those records is a little bit more complicated, right? You end up having to do the reduce function. So here we call reduce. We pass it a function, which is basically what we do with it. That function takes the record itself, an accumulator, which gets passed on the chain. And then I is basically an initialization value, right? What do you start with for the very first element? What does the accumulator equal? Or we can say get matching records. And again, like with get matching records, I think this is pretty straightforward with the filter function. You can do while loops, obviously pretty trivially in the recursive style. In this case, we do while, we pass it a function where we do stuff, and the idea is that function returns something that evaluates to either true or false. So if we were to define the while function, it looks like this. It's really simple, right? Which you don't even need to do these things if you actually get to the point where you're comfortable using recursion to do loops. Loop some specific number of times. So we could define a loop function where we just say, OK, loop this function, like call this function X number of times, right? So there's what the function call looks like. If we were to define that function, it would look something like this. Loop, which takes a function the number of times. It's going to call this separate function called loop until. And then loop until is the recursive definition, right? The function, the iteration you're on, the number of times. You check for it to see if you've already gone over the number of times. If you have, then you don't call it again. Otherwise, you call the function, and then you call loop, incrementing the number. All right, I'm a little over time. I will run a little over time, but I'm close. So finally, there's some syntactic sugar that we're thinking about adding to the language. So these things could always be added later. One thing I'd like to see is basically like a faster way to specify range and filter arguments to be able to pull back data really, really quickly. That's like the 80% use case for queries. So the example I put up is you have a stream object, right, which is just a collection of tables, and then you do an array index around it, And then there are 3 different elements in the array index. There's a predicate, which matches against the metadata. There's the time range. And then there is a list of strings, which are actually the columns that you want to pull from that stream. So here's an example. Basically, the from function gets us the stream, right? We're pulling from the foo bucket, and then we do the array index. The predicate is the CPU measurement, the usage user field, the time range in this case. So the time range is basically a start and a stop time. So we specify, the start date, 2018 1107 to 1108. And then finally we say these are the columns. The long form version of this looks like that. So from the filter with the predicate, the range, and the function called keep, which just says to keep these columns in the resulting tables. So here's a much more short one, which is basically just get me the last value from the CPU measurement, right? So from, and then the matcher is there. So the other 2 elements in the brackets are basically just left off, right? So the top piece is equivalent to the bottom piece. You could also put the columns in there if you care about it. The other thing is you could specify, basically there's no requirement that tag keys are a continuous stream of characters. You can have special characters in them and stuff like that. So you can wrap this in quotes. So what that means is in this predicate, in the brackets, the left-hand side of these equality operators is always going to be a tag key. Here's just the last hour worth of data, right? So the start and the stop time in the time range part of it can actually be time literals or duration literals. And if you don't put the colon, then it just assumes like, okay, you're just looking at the start time. So another one I'm looking at is basically some shortcut syntax for calling functions when the argument name matches a variable name that you have, right? So here's a pretty trivial example. We're assigning bucket equals foo, start equals -3. So the way you call it without the shortcut syntax is basically that first one, from bucket, bucket, range, start, start, right? So you see there's like a stutter when you're calling the functions, which I think is kind of ugly. So the idea is if the 2 are the same, you can exclude that and you get something that I think reads a little bit better, where you're calling from, bucket, range, start, and then you can specify the end. So we're going to have Flux office hours tomorrow. Nathaniel, the lead developer on Flux, is right there. So he and I are going to be in the room debating with each other and hopefully talking to all of you about some of these language design concepts and what we want to do is we want to optimize for usability. We want people to understand the language and for it to not be, we want the cognitive load to be as small as possible to learn and pick up the concepts. So InfluxDB 2 status. We released Alpha 5 last week. We're going to continue to release alphas. We have no set amount of alphas that we're going to release. The idea is during the alpha stage of the project, we're continuing to do feature development. We're not doing any performance work. That's not the goal. The goal is to iterate on features and to get feedback from the community about the stuff we're building and the things that they feel are very important to get in the first release of 2.0. Once we're actually happy with some minimal feature set, then we'll move into the beta phase. And the beta phase is the point at which we're doing bug fixes and performance. So Cloud 2, so at the same time as we're doing all the open source development, we're also developing our cloud products. We are launching the private beta, which is basically invite only, of Cloud 2 later this week. Tim will be talking about that. So from an API perspective and from a Flux language perspective, we're still at a point where we're probably going to make breaking changes. Hopefully nothing big. But our goal is in the next 4 weeks, we're going to get to a point where we don't need to make any breaking changes anymore. we'll certainly make additive changes, but hopefully not breaking ones. So I'm definitely looking forward to talking to as many of you as I can and hearing about what you think. All right, thank you.